Hi. I'm gonna try to go over like a summary of a majority of the stuff you guys covered this semester. I'm not gonna emphasize stuff that was covered in 112A because that would make me have to sit here talking for even longer. And if you really want to review that stuff, I have videos in a playlist on my channel from like my 112A worksheets. So there's that in your notes. And I primarily geared like this review towards Brooke's class because Samako's class doesn't have to take the exam. I mean, there's a lot of overlap, so this isn't going to be useless. I'm just saying, like, if there are details Samako covered that Brooke didn't, I might not necessarily have them here. And that's not to say that I'm not going to like get every single detail Brooke had. So like, this isn't going to be completely comprehensive. It's just gonna try to hit the main points so you can kind of get a refresher if you haven't already. Okay, so I'm gonna go in order. I'm gonna start by talking about aromaticity, which is basically just benzene rings, but like in terms of aromaticity, you have to be able to determine if something is aromatic. That might be something you're asked about. So like in order for something to be aromatic, it should have the Huckel number of electrons. That's the 4n plus 2 rule. I'll give examples in a minute. It has to have that number of electrons. It should be cyclic. It should be planar, which just means it's flat. And it should be conjugated. And n here can be any number. It can be 0, 1, 2, 3, 4, whatever. Just like it's any number that like if 4n, like if the number of pi electrons you have is equal to something with that value, then it works. And it's really hard to describe that, but I guess I'll show in a second like what works and what doesn't. So like this is benzene. There's two electrons in each pi bond, and there's 3 pi bonds. So there's 6 pi electrons here. It's a cyclic structure. It's conjugated, and conjugated just means that there's alternating single and double bonds. That's a topic that comes up multiple times in the semester, so that's good to be comfortable with. There's a single bond between each double bond here. And I just said there's 6 pi electrons. If n equals 1, then 4n plus 2 equals 6. So this has the right number of pi electrons. That's aromatic. So yeah, that's aromatic. If you drew this, this also has free pi bonds. It has the right number of pi electrons. It's cyclic. It's almost conjugated, but in order for something to be aromatic, like the whole cyclic structure has to be conjugated. Like basically the pi electron on the left here is not connected with the one on the right, so it's not completely conjugated. There has to be something up here to basically complete the loop. So it has like, and it's also probably not planar, but because it's not conjugated, this wouldn't be aromatic. This would be called non-aromatic. And I'm only going to cover like 3 examples here, but you could be asked a lot of different things. But this is one last one. There are 4 pi electrons in this structure, and it's cyclic, and I guess you can assume it's planar, but because it has 4 pi electrons, not 6, it's not a Huckel number of electrons, so this like has the rules for aromaticity besides the number of electrons, so this would be anti-aromatic. You could have a wide variety of questions about this kind of thing, but it's always the same kind of rules. You're just looking for these characteristics. And you can basically assume it's going to be planar or flat unless you're given something like just like a three-dimensional structure. Basically, if it's drawn as 2D, you can assume it's planar unless you're told otherwise. And then like you should be able to name benzene rings or be able to draw them if you're given a name. And also understanding like designations of things like in relation to each other. So if you draw a benzene ring and the circle there is just showing it's conjugated, I've done that all semester, so hopefully people understood that that's what it means. If you have two substituents right next to each other, like with a 1-2 relationship, they're going to be ortho to each other. If they have a 1-3 relationship, like here, then it's going to be meta in terms of those two. And then if they have a 1-4 relationship, they're para. And just like there are some common names, like if you have a methyl group on a benzene, that's called toluene. I'm not going to go over every single common name thing, but I'm just going over like the topic. There's stuff like toluene, there's stuff like styrene if you have an alkene attached. There's benzoic acid if you have a carboxylic acid attached. There's aniline if you have an amine, and there's more, but these are just some examples. So that just helps you either identify names, or if you're told like toluene is reacting with whatever reagent, then you know what toluene is, so you can figure out how the reaction is going to go. Naming is basically just like similar to naming linear structures. Like you number from the highest priority substituent to the lowest priorities. Like if I had a methyl group and then maybe a chlorine or something, you'd either want to number the methyl group or the alcohol one here, just so you can have like them having a 1-2 relationship to each other, so you have like the lowest possible number. I think in this case, you'd want to number it like this, just so you can give the chlorine the lowest possible number as well. If you numbered it with the alcohol as 1, then the chlorine would be 5. So you could call this toluene, and then you would say that there is a hydroxy on 2 and a chlorine on 4. So this would be 4-chloro 2-hydroxy toluene. And if you have multiple substituents like this, you don't want to use the ortho-meta-para designations when you're naming it. You can say that the alcohol is ortho to the methyl group, but you can't say like ortho hydroxy here because it would be confusing. So you should use numbers only if there's free substituents. You talked about reactions with benzene rings, and one of the ones you talked about a lot was electrophilic aromatic substitution. So in that, you would have a benzene ring, and one of the carbon-carbon double bonds would act as a nucleophile, and it would attack an electrophile. So I'm just going to show like a generic mechanism for this. Sorry. So I'm just going to put E plus for any generic electrophile. A double bond will be attacking it. And when you do that, you have the electrophile attached, and there's a hydrogen there still. And there's still a hydrogen here, but now this carbon only has free bonds, so it's positive. And a majority, well, like all the time when you're doing these, kind of something you use to form that electrophile here ends up leading to a base forming, and then the base can take this proton and do like an elimination step, basically. So I'm just going to put B for whatever that base is. And this is just an elimination step, sort of, to reform a double bond, and you get the benzene ring back. And all of the electrophilic aromatic substitution mechanisms will look like this. The only difference is what this electrophile would end up being. And if there's ever stuff on the ring, then that will influence where stuff gets added, but it's always going to look the same with these two steps. There are some directing effects. If you already have something attached to a ring, and I'll go over like identifying how stuff, or how you can figure out how stuff directs in certain directions. An alcohol is a electron donating group because it has lone pairs on it. So if something has a lone pair on it, then it's going to be ortho or meta directing, or ortho or para directing. And that is because if I show this bond attacking an electrophile, that puts a positive charge right below the alcohol, and there's a lone pair on it, so it can do a resonance form and basically pull the positive charge out of the benzene ring, which will stabilize the positive charge because resonance makes stuff more stable. And the same thing will happen if it gets added meta or para. So I'm just gonna draw that down here. This wouldn't be happening at the same time. I'm just trying to save time. So if it got added para, you'd have a positive charge here. You could do one resonance form, and that would end up putting the positive charge below the alcohol again. And then once it's there, you get that same resonance form I showed up here. So I'm not going to draw that, but it's the same idea. Just the resonance stabilizes the positive charge because it goes below the alcohol. If you add the electrophile meta to the alcohol, then you don't get that resonance forms yet. It's less stabilized, and that's just not ortho. It's not meta directing then. If you have something with a partial positive or a full positive charge, so like a nitro group has a positive charge on a nitrogen, which would be attached to the benzene ring, that's going to be meta directing, because if you add something ortho to it, I'm not going to show, but like it's the same idea as I just showed on the last page. If it's added ortho or para, you get a positive charge here. And putting a positive charge next to a positive charge, which I'm talking about this one, that's not very good. That's not stable, so you don't want to do that. But if you add it meta, then the positive charge basically skips the spot below the electron withdrawing group. So I'll go ahead and show it attacking here. And yes, the benzene rings are ugly, but hopefully you can get the idea. So when you draw these resonance forms, you can see like the positive charge just skipped over the spot below the nitro group, and I can draw one more. It's going to end up going down here, but it doesn't go below the nitro group. So that makes it like it doesn't have that particularly unstable resonance form. So stuff with a partial or full positive charge is meta-directing. And these things are also, like, they're withdrawing electrons from the ring because they have that positive charge. And by withdrawing electrons, they're making the benzene ring less nucleophilic, so it also makes the reaction go slower. And there's a trend, or like a, I guess, figure for like the reactivity of typical substituents. So on the far left, there's like nitro groups. There's tertiary amines that are positive. There's sulfonic acids. And you've also got like carbonyls, where the carbonyl oxygen is bonded to the ring. These are all pretty strong deactivators, and they're all meta-directing. And around here, you have halogens. That's what X is. These are ortho-para-directors, and they're weakly deactivating. Spelled deactivating wrong, but you get the idea. And then you have R groups, which are just alkyl groups. You have stuff like either like an oxygen or a nitrogen attached, and then it's also attached to a carbonyl. Those have lone pairs that are ortho-para-directing, and they're, because of that resonance I showed, like with the alcohol, they're stabilizing stuff, speeding up the reaction. It's like all of these are ortho-para, and they're activating. They make reactions go faster. So in terms of like the point of this, going from left to right is increasing activation strength. And if you have multiple substituents on a ring already, then they have competing, like where they're trying to tell stuff to go is kind of competing sometimes. So you have to figure out which one out of the two is a stronger activator, and then that's going to win in terms of directing effects. So like if I have benzene ring with an alcohol, that's an ortho-para director. And then I've got a nitro group here. The nitro group is directing stuff to go meta to it, which in this case is just this spot. And then the alcohol is directing stuff to go ortho or para to it, which is these boxed spots. The alcohol is an activator, while the nitro group's a deactivator, so the alcohol is going to win. And stuff is probably going to get added here and here. Not at this one because it's hard to add stuff between two substituents, but the other two stuff will get added to. So just stronger activator wins, and you can refer to the chart I just drew for like activation strength. And if two things have basically the same activation strength, like two alkyl groups, then you can consider like which one is more bulky, because that will also kind of slow down a reaction. So this isopropyl group is more bulky than the methyl group. So stuff's probably going to get added up here next to the methyl group, just because it's easier to add stuff there. And just some examples of some EAS reactions you've seen. You can do like Friedel-Crafts reactions, either with just an alkyl group with a chlorine or an acyl group with a chlorine, and then that was done with AlCl3. That will just put either the alkyl group by itself or like a carbonyl on the chain. You could add like halogens with Cl2 and FeCl free. And there are some other reactions, but hopefully just this jogs your memory if you haven't looked at it in a while. I'm not going to go over all of them. I don't have the time to go over every single thing. Those are some examples. Another type of reaction you can do with benzene rings is nucleophilic aromatic substitution. So there are like 3 ways you can do that, adding nucleophiles to a benzene ring. You can either form an N2 plus leaving group, and you would do that by, like, you would start by putting a nitro group on the benzene ring, and then you have to reduce it to form an amine. You can do that with a bunch of different reagents. You can use zinc and hydrochloric acid, or tin and hydrochloric acid, or basically a lot of different metals, or like hydrogen and palladium. Like all of these will reduce a nitro group to an amine. And then if you treat an amine with HNO2, that's going to turn it into an actually, I don't think it's called an azide, but it forms an N2 that has a plus charge on it, and this is a pretty good leaving group. If you treat this with a bunch of different things that have copper, there's a lot of them. I'm not going to go over all of them, but like you can treat it with copper and iodine, and I will just replace the N2 with an iodine. You can treat it with a copper and a cyanate, and that'll replace the N2 with a nitrile. And then the kind of oddball is if you just treat it with water, you get an alcohol. Again, these aren't all of them, but these are just some examples to get like some nucleophiles attached to a benzene ring. There's also 2 kinds of mechanisms that you might need to know for nucleophilic aromatic substitution. There's one where you basically either heat a benzene ring a lot to make something very unstable form called benzene. So like if you, or you can use NaNH2, and I'm gonna go ahead and show it with that. So this is a very strong nucleophile. And nucleophilic aromatic substitutions all require a leaving group. The one I was just showing a minute ago, the leaving group was N2. Here the leaving group's going to be this halogen, and with the other 2, it's pretty much always going to be a halogen. This is basically an E2 step. And when you do this, you end up forming a triple bond here. And that's the benzene intermediate, and then another NH2 can either attack up here or down here. It can attack either end of the triple bond. And when you attack, like I'll just show it's attacking this top one, but it can do both. If it does that, you get an NH2 here, and then you would end up with a negative charge here. And that's just gonna get protonated to get rid of the negative charge. And you in the end, you replaced the bromine with an amine. But like I just said, it can also attack the other end of that triple bond. So you're also going to get this product. So you can either do this by adding NaNH2 to a benzene ring where you have a leaving group like a halogen, or you can do like molten sodium hydroxide, just like a lot of temperature and sodium hydroxide, and then you'll end up getting 2 of these products because of that triple bond. So And this is the mechanism of how that happens. So just benzyne leads to two products. I spelled products wrong, but you get the idea. And the other nucleophilic aromatic substitution mechanism is, I think it's just called like nucleophilic aromatic substitution, SNAR. It requires an electron withdrawing group, so like a nitro group or a carbonyl or a sulfonic acid, to be ortho or para to a leaving group. So an example would be like this structure here. The nitro group, which is an electron withdrawing group, is para to this leaving group, the bromine. And if we're using hydroxide as our nucleophile, it can attack the spots where the bromine is. And I'm just gonna show like how the electrons can flow and why that matters. If you show all of those electron flows going up to the nitro group, then basically like you're adding electrons to the benzene ring with the nucleophile, but because the nitro group withdraws electrons, it basically stabilizes those extra electrons that we just added. Because if they weren't stabilized, then there would be a lot of excess electrons in the ring, and it probably wouldn't be happy. And also, this would happen. There are negative charges on these. I haven't been drawing them, but there are. And then the rest of the mechanism is basically just the nitro group reforming, the electrons going in the opposite direction. So you can kick out the leaving group. You don't really, I don't think you have to show this whole thing. Maybe you could theoretically just show like the hydroxide adding and the bromine getting kicked out, but like this electron flow explains why having the electron withdrawing group, ortho or para, to the leaving group makes this work. So the first step was just addition of the nucleophile, and then the second step is the electrons coming back down to reform a double bond and kick out a leaving group, and that's elimination. And the end result is just replacing the leaving group with the nucleophile. In this case, an alcohol. And you can do that with a lot of different nucleophiles. You just have to have electron withdrawing group, ortho or para to a leaving group. So you could do it with hydroxide. I think you could do it with a cyanate like CN minus, probably amines, just like any nucleophile that's pretty strong would probably work. You just have to have that condition to do this mechanism. And those are the ways you can get nucleophiles onto a benzene ring, which differs from the electrophiles. And then there were also some side reactions you covered. I already talked about turning nitro groups into amines by reducing them. Also, and I didn't point this out earlier, so I guess I will now. If you have either an NH2 or I'll just put all of them. If you have an NH2 or a strong electron withdrawing group, like a nitro group or a sulfonic acid, and you try to do Friedel-Crafts reactions, like with RCl and AlCl3, hopefully remember that these all stop the reaction from happening, so that's a detail that is good to know. Like if you're trying to do a synthesis with a benzene ring, and one of the steps is going to involve a Friedel-Crafts step, adding like an alkyl group, you can't have any of these on the ring first. So you have to consider that for like the order you're going to take. Also, if you have a carbonyl at the benzylic position, which is the spot here right next to the benzene ring, you can reduce it with conditions that don't normally reduce carbonyl. So this doesn't normally happen, but if it's benzylic and you use these conditions, then the carbonyl gets reduced and you're just left with an alkyl chain. So that's a side reaction you covered. if you have a benzoic hydrogen, again, benzoic is just this spot here right next to the benzene ring, and you react something that has at least one benzoic hydrogen with NBS and HNu. This does a radical reaction that I'm not going to cover the details of, but it just ends up replacing one of the hydrogens with a bromine at the benzoic position, and then you could do more stuff with that bromine. And also, if you have a benzoic hydrogen and you treat this with KMnO4, it will turn the benzoic spot into a carboxylic acid. So these are just some examples of, like, these don't really fit into those other two categories I just talked about, but they're still aromatic reactions. They're still relevant to this part of the class. Next is alcohols. Kind of just going in the order of stuff that was covered. Some stuff about alcohols. The naming is similar to stuff you did in 112A, and you've been doing nomenclature all semester, so it's not too complicated. Just you use the OL ending for the parent chain. It's like here are the alcohols on carbon 2, so this is just 2-butanol. The OL ending is for the alcohol. Some ways you can synthesize alcohols. You can synthesize them by oxidizing alkenes. It's like this alkene. If you did the mercury acetate reaction, like Hg and these conditions, that's going to put the alcohol on the Markovnikov spot, which is the more substituted spot. So you'd get this alcohol. This is an O, not E. And if you treat it with BH3, this is supposed to be a 2, then that will put the alcohol on the anti-Markovnikov spot, so the less substituted side here. So these are some ways you can form an alcohol. You can also form an alcohol from like SN1 and SN2 reactions, and which one you decide to use depends on your substrate. It's like this is a tertiary substrate, the chlorine is on a tertiary alcohol, or a tertiary carbon. So you'd want to use an SN1 mechanism to do this. That would just involve adding water with acidic conditions. I'm not going to go over the mechanism, but it's just SN1 because it's a tertiary substrate. If it's secondary, it can theoretically go either way. But if it's tertiary, it has to be SN1 if you want it to work. And if it's primary, then you're going to want to do a SN2 mechanism. So like if we have this, that's a primary alkyl halide. And then you can add hydroxide to this to do an SN. This was SN1, this is SN2. You can do an SN2 here to just replace that with an alcohol. And some other ways to form alcohols is reducing carbonyls. So you could either add a Grignard to this in one step and then acid in the second step. Or you could also add like a hydride from LiAlH4 or NaBH4, one of those hydride reducing agents. And that'll end up giving you an alcohol. And then whatever you add is either a hydrogen or an alkyl chain. Either way, you formed an alcohol. I'm just going over like how you're synthesizing them. And then one other way you can form alcohols is adding nucleophiles to epoxides or cleaving ethers, which I'm also going to be talking about later anyway. But like if you have an ether and you add H3O plus to it, then you're going to end up with 2 alcohols here because you just cut the ether in half basically. And if you have an epoxide and you add hydroxide to this, the hydroxide would like attack there. And then you could protonate the O- that forms, and you would end up with this, just some alcohols. Again, just some general ways to form alcohols as a sort of review. Some notes about alcohols that might be good to know. Like, a chlorine is a good leaving group, and halogens are good leaving groups, so you can do nucleophilic substitutions with them, and they're fine. Because when you do that, you form a Cl minus, and it stabilizes the negative charge because halogens are happy with a negative charge. But alcohols are not good leaving groups, because if you kick them out, you end up with a hydroxide, and hydroxide is not stable. It's pretty reactive, so it's probably not going to leave very well. So you have to do stuff to alcohols, like either turning them into a better leaving group or just replacing them with something else first before you can do nucleophilic substitutions with them. And some ways you can do that are like, you could react this with, I'll do it on another slide. You could like use SOCl2 just as one example to turn this into a chlorine, and then the chlorine is a good leaving group, and you can do nucleophilic stuff with that. And nucleophiles are also weak, or alcohols are weak nucleophiles, so you have to deprotonate them with a base to turn them into a good nucleophile. You can do that with sodium hydride. That's pretty common. That will form a negative charge on the oxygen because it takes the proton. And then this is a good nucleophile, and you can use it for SN2 reactions. And generally, the SN2 reaction you do with it is reacting it with like an alkyl halide. And that, again, that's just an SN2 reaction, and that will form an ether. And this kind of thing where you're doing an SN2 reaction to form an ether is called Williamson ether synthesis. So that's a way to form ethers, and that's how alcohols can indirectly act as nucleophiles. And I'm probably going to repeat this later, but again, this is an SN2 reaction, and SN2 require either primary or secondary substrates. If it's a tertiary substrate, an elimination reaction is more likely. So if you're going for a nucleophilic substitution, you're going to want it to be primary or secondary, if that's what you're going for. So that's just like a curveball that might be thrown at you. If you're given a tertiary alkyl halide, you're not going to get an ether here. You're going to get a carbon-carbon double bond, probably. Some other things you can do with alcohols is oxidize them. So if you have a primary alcohol, it doesn't matter what you use to oxidize it. So I'm just going to put O for like general oxidation, and I'll list some of the reagents you can use in a minute. But whatever you use, it's going to end up forming a ketone if it's a secondary alcohol. And the way you can determine it's secondary is you look at the carbon the alcohol is attached to. That carbon is attached to two other carbons, so this is secondary. This would be primary because the alcohol, or the carbon that the alcohol is attached to, is only bonded to one other carbon. If you use a strong oxidizing agent like a chromate, CrO3, or if you used KMnO4, that's going to completely oxidize it to give you a carboxylic acid. But if you use a weaker oxidizing agent like PCC, then it's only going to partially oxidize it to form an aldehyde. So it kind of depends what you're going for, which one you decide to use, but no matter what you use on a secondary alcohol, we'll get a ketone. And if you have a tertiary alcohol and you try to oxidize it with anything, at least as far as this class is concerned, nothing happens. So you can't oxidize a tertiary alcohol. Okay. So yeah, that's all I'm gonna say about alcohols. I already discussed how you can form ethers by reacting alkoxides with alkyl halides to do that SN2 step. So this would be one kind of ether you could form. It's just an oxygen attached to 2 carbon chains. And there's only one reaction you guys learned that ethers do, and it's acid catalyzed cleavage. So you're just adding an acid. The acid, most of the time, is probably either going to be like H3O plus or HCl or something. If it's H3O plus, you're going to form 2 alcohols. And then you don't really have to worry about the mechanism it's going to follow, because like it's just going to be 2 alcohols on both sides. You don't have to consider what's going to go where. But if you have HCl or HBr or any other kind of acid besides H3O plus, then you do have to consider like this cleavage could either be SN1 or SN2. And how it goes depends on both sides of the ether. So you should look at like if they're primary, secondary, or tertiary. On the left side, this is tertiary. On the right side, it's secondary, not, yeah, it's secondary. Or maybe, yeah, I'm pretty sure that's secondary. It would be considered that. So the first step is always going to be the same. It's just going to be the ether getting protonated. Actually, okay. Okay, so we have an OH plus. This can be a leaving group now. And because we have one tertiary and one secondary spot, this is going to end up following an SN2 kind of mechanism, because one of the spots favors an SN2 mechanism while the other one doesn't really have a preference. So that's just going to end up going like this. It's going to form this alcohol, and then we get this cation. And then I'm just going to say we're using HCl here, so then the nucleophile comes and attacks the cation, and that's where the chlorine ends up in this case, because it was SN1 because of this tertiary spot. However, if you have something like this, where one spot is primary and the other spot is secondary, then it's going to want to do an SN2 kind of mechanism, because one spot favors SN2, the other one doesn't have a preference. So again, we're going to protonate it. That's going to lead to this forming, which can be a leaving group. And in this case, because it's SN2, the nucleophile is going to attack the primary spot. It's going to kick out the leaving group. And we end up with, that is where the nucleophile attached, CH3, Cl, and then we end up with this alcohol. So I could go over a lot of examples of this, but just look at both sides of the ether. If one of them is tertiary, the other one, well, if one of them is tertiary, it's probably going to do the SN1 mechanism. If one of them is primary, it'll probably do SN2. I don't think they're going to do something that's supposed to be a trick question, so it's probably going to be obvious. And that's all ethers can do. But there's also epoxides, which look something like this. They just have like a sort of free-membered ring with an oxygen, and these are a type of ether. And these can also be cleaved with acid like ethers can, and that would go the same way. You'd follow the same general steps I was just following to figure out like what the mechanism does. You can also cleave these with a base like hydroxide or any other strong nucleophile like a Grignard or hydride or whatever. So I'm just going to use Nu minus for like a generic nucleophile. And this is always going to do an SN2 mechanism, so it's going to attack the less substituted side. In this case, that's this spot, because that's like a secondary spot while the other one is basically tertiary. So it does this SN2 step. And you end up with an O minus. So when you do this, you have to do a second acid workup step. I'm just going to put this to show like that's what would happen in the second step. And you end up with an alcohol and your nucleophile attached. So just again, this is always going to be SN2 if you're cleaving an epoxide with a base. Okay. You guys talked about phenols a little bit. All I'm going to say about that is if you deprotonate a phenol, you form this O minus. And this O minus is more stable than a regular O minus would be because it has these resonance forms, and I'm not going to draw all of them, but just the fact that it's right next to a benzene ring shows that it has resonance forms. Resonance forms stabilize the negative charge, so the base is weaker, the acid was stronger, so phenols are relatively acidic. That's all I'm going to say about them, I guess. That's all I think you would have to know that you didn't really think about most of the time already. Brooke talked about phials and sulfides. You can try to form a phial, which is basically just a sulfur analog of an alcohol. You can try to form them from an SN2 reaction, like with an alkyl halide. It's like, here's an alkyl halide. And you could use NaSH, so SH with a negative charge. That would do an SN2 step. But the problem with this is a phial is a pretty strong nucleophile. So it's going to react again. It's going to react with another alkyl halide. And there's not an easy way to stop this, so you end up with a sulfide if you try to form a phial from a SN2 reaction with SH minus. If that's what you want, then this is a way to form them, but if that's not what you want, then you have to do something else to form a phial. So the way that Brooke presented making them is you, instead of using SH minus as your nucleophile with alkyl halide, you can use this structure called phial urethra or urea. It looks like this. I don't think you have to know the name of it, but maybe you should be able to like recognize it. And I'm not gonna go over the mechanism. I'm not sure if you guys have to know that, but it is in a lecture somewhere from earlier in the semester. It just involves reacting this with an alkyl halide in one step and then adding hydroxide in a second step. And that's basically just going to replace this alkyl halide with a file. So you're going to end with this. And one other thing you can do with files, if you add I2 to them, that's going to oxidize them and it's going to form a disulfide. So it's going to form this disulfide. And you can reverse this reaction by reducing it with common reducing agents. And one example that he gave is just CN and HCl, but you could probably use like hydrogen and palladium and other common reducing agents. And then I already discussed you can form sulfides by reacting a thiol with an alkyl halide. So I'm talking about sulfides now. That's a way you can form sulfides. And sulfides also still have lone pairs on them. So I'm not sure if you have to worry about this, but he did bring it up. They're still okay nucleophiles. It could still react again, potentially. So if it reacted with another alkyl halide, then you could get this, which has a positive charge on it. And it's called a sulfonium salt. So just like the files kept going, a sulfide could also potentially keep going and react further than you want it to. And one other little detail that he brought up about sulfides, if you add an oxidizing agent like hydrogen peroxide, H2O2, you can oxidize it to form a sulfoxide, and you can react that with more hydrogen peroxide to oxidize it even more. There's a positive charge here. That'll put another oxygen on it to oxidize it further. So this first one is called a sulfoxide, and then this last intermediate or product is called a sulfone. So that's oxidizing a sulfide bond. Next, he talked about amines. I kind of discussed identifying primary, secondary, and tertiary alcohols, and the rules for alcohols versus amines are different. So like this alcohol, to determine if it's primary, secondary, or tertiary, you look at the carbon the alcohol is attached to. That carbon is bonded to two other carbons, these two. So that's a secondary alcohol. But if we draw the same kind of structure, but with a nitrogen instead of an oxygen, this is a primary amine. Because the way you determine what an amine is you look at how many carbons the nitrogen is attached to. This nitrogen is only attached to one carbon, so it's primary. Just as some other examples, if we drew this, that nitrogen is attached to two carbons, so this is secondary. And this nitrogen is attached to three carbons, so it's tertiary. All of these are neutral, but quaternary amines are also a thing. So if you have a quaternary amine, it's going to have a positive charge. And yeah, that's just quaternary. Just look at however many carbons are attached to the nitrogen to figure out what it is, which differs from alcohols, like I just said. Amines can act as bases, so like you could theoretically just do any acid-base reaction with an amine. I'm not going to give an example, just they can act as bases. And similar to files where, like, I'll show the same kind of setup too. you might think, just like you would have thought, like you could synthesize a file of NaSH. If you want to form an amine with NaNH2, you're going to do an SN2 step, and you're going to end up forming this amine. But this amine still has a lone pair, and it's still a good nucleophile. So it's going to react with another alkyl halide to give you this. That still has a lone pair. It can react with another alkyl halide to give you this. So like first we formed a primary amine, then we formed a secondary one, then we formed a tertiary one. And it still has a lone pair, so it can react again. And you can end up with a quaternary ammonium salt. So SN2 with NaH2, or like amines just by themselves in general. This doesn't really work because it's hard to stop the reaction at a particular product. It's probably going to form like a mixture of all of these products, and that's not what you usually want to happen. But there are other ways that you can form amines, and some of them involve SN2 steps. So like if we take that same alkyl halide and we react it with NaN-free, this has a negative charge on the N-free, so that is a nucleophile. It can do an SN2 step and replace the bromine with N-free. And then if you reduce this with LiAlH4 and acid, that's gonna give you an amine. Oops. So this is a primary amine. And you can also use a cyanate to do an SN2 step. That'll form a nitrile, and then you can also use LiAlH4 to reduce it again. It's the same steps. And this also forms a primary amine. If you use a cyanate to do this, you're adding a carbon in the process. Well, you didn't do that with the N-free, so that's a detail that kind of tells you which one you should use if you're trying to synthesize something. Another way you can form amines is with this structure. It has a name, but I doubt you guys have to know it. But if you add a base to this to take the proton here, so like in the first step, you'll add a base, something like hydroxide or hydride. That's going to take this proton, form an N-, then you have a nucleophile. And then you can react it with an alkyl halide in an SN2 step. And then in the last step, you're adding something to basically make this nitrogen. And I guess I'll draw the intermediate. But so after the first two steps, you end up with this intermediate because the nitrogen did an SN2 step with that alkyl halide. And then in the last step, you basically just want to make this thing leave. And if you look at either this top part or the same part like with the other carbonyl, this looks like an amide because it basically is an amide. So you could add like sodium hydroxide to this and heat it. And as you guys know, because you've gotten that far in the class now, if you add like hydroxide or water to an amide, it's going to turn it into a carboxylic acid and kick out the leaving group. So that's what happens here. They're going to form, well, because we're adding hydroxide, we're going to form carboxylates instead of carboxylic acids, but it's the same idea. And then you end up with your amine. And that's what we care about here. And that's another way to form amines. You can also form them just by reducing amides. with LiAlH4 and acid, so that's just going to leave you with the nitrogen and basically get rid of the carbonyl. So that's a way to form amines from amides. If you do it with an amide like this, with just an NH2, that's going to give you a primary amine. If you do it with an amide like this, these quotes are just saying that's the same conditions. That's going to give you a secondary amine. So those are just more ways to form amines. The one last way that wasn't covered when he did this during that part of the class, I think, but I'm going to cover it soonish, but this is an imine. It has a carbon-nitrogen double bond. And if you reduce this with LiAlH4, I'm just going to put LiAl and acid, then that will reduce it and, oh, actually, it should be like this. Yeah, once you reduce it, it basically gets rid of the double bond, and this is a tertiary amine because it has free carbons bonded to the nitrogen. So I think this is the only way that you guys know to form a tertiary amine, at least like without that mixture of products with the SN2 step with the amines that I showed before. So this might be good to be aware of. If you're trying to synthesize a tertiary amine, you should maybe consider trying to get an imine, that's what this is, and then reducing it. Okay, next on the list is aldehydes and ketones. This is a ketone. This is an aldehyde. I'm sure you guys know that, but just going over it. It's a ketone if it has alkyl groups on both sides of the carbonyl, and it's an aldehyde if it has one, or if it had two hydrogens, this would also be an aldehyde. Just like a hydrogen attached to a carbonyl carbon, that's an aldehyde. Both of these have similar reactivities and reactions. Because a carbon is less electronegative than an oxygen, you have this dipole, and you also have a resonance form like this. And it's the same thing with the ketone. So you end up with a negative charge on the oxygen and a positive charge on the carbon. So like based on that dipole and this resonance, the oxygen is a nucleophile and a base, and the carbon is an electrophile. So depending on what you react these things with, they might react differently. If you add like an acid or an electrophile, it's probably going to react up here with the oxygen. If you add a nucleophile, it's probably going to add here. So like I said, it just kind of depends on what you're reacting them with. But a lot of the time, like you're either adding an acid or a nucleophile. I don't think there are any instances where you like add an electrophile and it reacts with a carbonyl oxygen, this semester at least. And in terms of naming, if I have a structure like this, you have to number the carbons if it's a ketone, so you know where the ketone is. This has 4 carbons, so it has the buttes. And you use the O and E ending for ketones, so this is 2-butanone. This has 2 carbons. You don't have to number it if it's an aldehyde. And if it's an aldehyde, you use the Al ending. So here, this would be ethane if it was just 2 carbons, because it has an aldehyde, it's FNL. That's the only difference there. And this doesn't usually come up, but if you have a higher priority group, like a carboxylic acid, then you have to call like a ketone or an aldehyde a substituent. So like here we'd call the ketone an oxo group. So the way you would name this is free oxo and butanoic acid. And I'll go over naming carboxylic acids briefly later, but it's just a carbonyl as a substituent is an oxo group if there's something else that's more important than it. Okay. In terms of forming ketones and aldehydes, I've already talked about oxidizing alcohols. So you have a primary alcohol, and if you want to stop at an aldehyde, which is what we're looking at right now, you'd want to use PCC. If you used a stronger oxidizing agent, you'd get a carboxylic acid. If you have a secondary alcohol, it doesn't matter what you use to oxidize it, you're going to get a ketone. So I'm just going to put this as like generic oxidation. So yeah, that's one of the more general ways to form ketones and aldehydes. The only other main way that I could think of when I was putting this plan together is just like reducing a carboxylic acid to an aldehyde. So to do that, you'd want to use diol H. Or you could reduce it all the way to an alcohol and then oxidize it if you forget about diol H. There wouldn't be anything wrong with that. But this is a way to do it in fewer steps. Just go straight from a carboxylic acid to an aldehyde. And those are ways to synthesize ketones and aldehydes. And then all carbonyls or all ketones and aldehydes are going to have similar reactions. They're going to do nucleophilic addition reactions. There's two general classes of nucleophilic addition reactions. There's base and acid catalyzed, and there are some variations in these that I'll go over, but in general, a base catalyzed mechanism, you're going to be adding something with a negative charge on the nucleophile. That's a very strong nucleophile in one step, and then in a second step, you're adding an acid. You don't have the acid in the nucleophile at the same time. And then the way this goes is the nucleophile attacks the carbonyl carbon. You get an O- intermediate, and then you have your nucleophile attached. And then in the second step, the O- gets protonated by the acid. And you end up with an alcohol and your nucleophile attached to the same carbon where the ketone or aldehyde was. So again, this is base catalyzed. And some nucleophiles that do this are Grignards, so like or MGBR, or the hydride reducing agents like NABH4 and LiAlH4. And then one other one is if you have an alkyl group attached to lithium that behaves like a Grignard reagent. These are just some really strong nucleophiles that will generally do a base catalyzed mechanism. There are some weaker nucleophiles that will also follow this kind of mechanism, but these are some of the common ones. And then there's also the acid catalyzed mechanism. And you would do this if you're adding a weaker nucleophile or one that has like a proton on it, which again would mean it's weaker. So I'm just going to put like Nu and an H to show like it's protonated, which also means it's generally weaker. And then you have acidic conditions. So because the nucleophile is weaker, it can't just directly attack the carbonyl carbon like I just showed with the other mechanism. So the way this starts is by protonating the carbonyl oxygen like this. That's going to make the carbonyl carbon a better electrophile because it puts a positive charge on that. And now this weaker nucleophile can come and attack the carbonyl carbon. But when it does that, the nucleophile still has its proton. It has a positive charge. this first proton here came from some proton source. So like if we say it's H4O plus, then when that happened, when it took the proton, it formed water. So water can just take that proton and then you reform the acid catalyst. But the point is, like, just the proton on that nucleophile has somewhere to go. And you end up with this kind of product, an alcohol and a nucleophile attached. Again, there are some acid catalyzed mechanisms that have more steps than this, but they generally follow these same steps. They just kind of repeat it 2 times, and I'll go over those when I get to them. So those are the kinds of mechanisms they can do. If you add either like a Grignard or a hydride reducing agent like LiAlH4, and then you add acid, that reduces these. It's like if you add a Grignard, then you would get an R group here. If you added a hydride, you have a hydrogen. And I'm just explaining this or bringing it up again because if you use these strong nucleophiles like Grignards or hydride reducing agents, then the reaction is irreversible. Pretty much all the other reactions that I'm going to go over after this with ketones and aldehydes are reversible. You can do something to make the reaction go back to the ketone or the aldehyde. But if you use a strong nucleophile like these or RLI with the lithium, then you can't go backwards, so you're stuck with whatever you form. So that might be good to know. In terms of like adding or doing like a base catalyzed mechanism, but doing it with a weak nucleophile, there are a few examples. I'm not going to show the mechanisms for these, but if you want to practice them, it's just they're all going to be base catalyzed until I say we're looking at something else. And you can tell, because do we have a negative charge on the nucleophile? If you add hydroxide to a ketone or an aldehyde, that's going to give you a gem diol, just 2 alcohols attached to the same carbon. And I'm going to actually erase this arrow because this has an equilibrium. And this equilibrium greatly favors the carbonyl, even if you have an acid or a base catalyst. And I think most of the other reactions also have like an equilibrium that probably favors the carbonyl, but like this one with the gem diol favors the carbonyl so much that you basically don't see the gem diol form, even if you have a catalyst. So I would say like be aware of this reaction and the mechanism to do it, which is just base catalyzed, but this probably isn't going to be a product of a reaction if you're looking at a question, as I'm going to say later, and as you probably are thinking, like if you add a base to this, the base can take a proton here to form an enolate, and then you could do an aldol reaction, so that's much more likely, and I'll talk about that later, but just this can happen theoretically. If you add a cyanate to a ketone or an aldehyde, which is just a CN minus, and I'll just say water is the proton source. You have an alcohol, and then you have your nucleophile. In this case, it's the cyanate, so you have a nitrile. This forms a cyanohydrin. Hopefully you can see the pattern, like all of these have an alcohol, and then you just add a nucleophile along with the alcohol for the product. So like with the Grignard, the nucleophile was an alkyl group, hydride it was a hydrogen. Here it's alcohols or nitriles. It's always the same kind of thing. Some other base catalyzed things with weaker nucleophiles if you add an alkoxide, a deprotonated alcohol, I will show the mechanism for this, but it's going to be the same mechanism that was base catalyzed before. I just want to show this to show the distinction. So you have the nucleophile attached, you have the negative oxygen, and then it's going to take a proton from the proton source. In this case, this is just an alcohol. R is just any alkyl group, if people were confused by that. It's just like a methyl group, an ethyl group, whatever. It's just some carbon chain. So you will end up with this product, and this is called a hemiacetal. It has an alcohol and an ether attached to the same carbon. And if you're adding an alcohol to a ketone or an aldehyde with basic conditions with a negative alcohol, it's going to stop at the hemiacetal. So I think I messed this up when I was covering it in the workshop, but like if it's acid catalyzed, it's going to keep going to something else. But if it's base catalyzed, it stops at the hemiacetal. So it only adds one alcohol. Similarly, if you add like an amine with non-acidic conditions, so let's just say water. I'm not going to show the mechanism, but it's going to look basically the same as the last one, just with the nitrogen as the nucleophile. You end up with this, and this is called an hemiaminal. Just like with the basic catalyzed addition of an alcohol, it stopped at the hemiacetal. With the basic conditions for adding an amine, it's going to stop at the hemiaminal, but it'll keep going to something else with the acid catalyzed mechanism, which I'll go over shortly. Just like if you add hydroxide to a ketone or an aldehyde, if you add water with acidic conditions, that'll do. And now I'm going over acid catalyzed steps. So if you want to draw these mechanisms that I'm not showing, it's going to be acid catalyzed. But this is going to form the same thing that hydroxide did. It's going to form a gem diol. And this has the same problem that the gem diol did before, just the equilibrium greatly favors the carbonyl. And there are probably more reactions that I'm not going to be like going over just because I'm not covering everything, but just like all the acid catalyzed mechanisms look kind of similar. But in terms of adding an alcohol to a ketone or an aldehyde under acidic conditions, so I'll just put HOR for a generic alcohol. And I'll put like H plus for acidic conditions. Because we have acidic conditions, this is going to be acid catalyzed. So the first step is going to be the same always if it's acid catalyzed. It's this to make the carbonyl carbon more electrophilic. And then the alcohol can go ahead and attack the carbonyl carbon. I should have shown the first arrow as equilibrium, but I'll just show this one as equilibrium because all of these steps are in equilibrium. They can all go backwards at any point. So now the alcohol that attached has a positive charge, and the proton has to go somewhere. The alcohol next to it can take that proton to get rid of the positive charge on the ether. That's going to form water where the alcohol was, and water is a pretty good leaving group. And again, this doesn't happen with the basic conditions, but it can happen with the acidic conditions of adding an alcohol to a ketone or an aldehyde. like because it's acidic conditions, you can do that proton transfer to form water. You can kick water out. And then when you kick water out, you're adding another alcohol. So you end up adding 2 of the nucleophile instead of 1. But like this was kind of repetition. Like the first step was protonation of this oxygen so that we could make the carbon a better electrophile. And then we added the alcohol to the carbon. And then we have 1 alcohol. And then again, we protonated this oxygen, which made this carbon a better electrophile. And then we added another alcohol. And in the process, we kick out the water. But it's basically just repeating the same steps again to add another nucleophile. So at this point, the nucleophile that just attached has a positive charge, and the water that we just kicked out can just take that proton that's sitting there. And we end up with an acetal. We end up with 2 ethers attached to the same carbon. And yeah, this is the mechanism. This is probably going to be good to know just in case it comes up, because this is one of the more tricky mechanisms this semester. In terms of like determining, or like, I guess I'll just draw this. I drew all of the arrows in that mechanism as equilibrium arrows. And if you're just looking at like the reaction by itself, like as a formula, it would look something like this. So if you want to make the acetal form, then you'd want to remove water, because if you remove water, then you're going to drive the equilibrium reaction forward and you're going to form more acetal. But if you wanted to reverse this reaction and turn the acetal back into a ketone or an aldehyde, you'd want to add more water. So that's why I drew this. Add water to reverse the reaction. And this is particularly relevant with an acetal because acetals are ethers. And as I said earlier, ethers only have 1 reaction. It's acid-catalyzed cleavage. So if you add true plus to this, just again, as like an example, you're going to form alcohols. But that's all you can do to ethers. That's the only reaction they do. They just get cleaved if you add acid to them. So an acetal is a protecting group for ketones and aldehydes. And only ketones and aldehydes. It's not gonna, like, you can't form acetals with any other functional group. So all of the reactions I've been discussing, I kind of said it, but like they only apply to ketones and aldehydes lately. When I get to a new topic, I'll say that, but until then, these just apply to ketones and aldehydes. And then similarly to how like the addition of an amine stopped at a hemiaminal for base catalysis, but there's a different kind of thing you can get if you're adding a amine with acidic conditions. So I'll go ahead and show that now. Here I'm starting with a primary amine because the nitrogen there only has 1 R group on it, so it only is bonded to 1 carbon. This is a primary amine, and that's relevant because it determines what kind of product you're going to get. The first step is going to be the same as it was with the acetal because this is acid catalyzed, so we're going to protonate the oxygen in the carbonyl. And then once we have a better nucleophile, or once we have a better electrophile because we have a positive charge, the amine can attack. Then it has a positive charge, but just like before, we can do a proton transfer to transfer a proton to the alcohol and form a better leaving group. Because that forms water once it gets a proton. This differs from the acetal reaction because instead of adding another amine at this step, like when we added another alcohol at this step, the lone pair on this nitrogen is going to basically do an elimination reaction to kick out the water. So that's different and that's annoying, but that's just kind of how it is. And now the nitrogen has a positive charge again, so we have to do another proton transfer. The water that just got kicked out can take that proton. And you end up with a carbon-nitrogen double bond, which I brought this up earlier. This is an imine. So you get this if you add a primary amine to a ketone or aldehyde. But only if it's a primary amine or if it's ammonia. So if you add NH3, you'll also get an imine. But if it's a secondary amine, it's going to be a little different, and I'll show that now. Okay, so first step, I'll draw the arrow with the conditions in a second, but it's going to be acid catalysis again. This time there's two R groups attached to the amine, so it's secondary amine. We have acid conditions again. So it's the same steps for the first few steps, like it's the same thing. Again, once the nitrogen gets added, it has a positive charge. We can do a proton transfer to the alcohol. It's going to form water. And then again, the nitrogen can form a double bond and do like an elimination step to kick out the water. But this time, well, the primary amine had another hydrogen at this step when it formed a double bond, so it could lose that hydrogen to get rid of the positive charge. This nitrogen doesn't have one. So what basically happens is you have to have a proton alpha to this carbon-nitrogen double bond, and then a base. In this case, let's just say it's the water that we just kicked out. It's going to take that proton and it's going to do this electron flow. It's kind of like an elimination reaction, except we're not eliminating anything. We're just, I guess we're eliminating the positive charge on the nitrogen, but we're just forming a carbon-carbon double bond. And this is an enamine. And it forms when you add a secondary alcohol, secondary amine to ketone or an aldehyde. Okay, so yeah, primary amine will give you an imine, secondary amine will give you an enamine. And they, like, you can also reverse these reactions by adding water, just like you could reduce the, or reverse the reactions with the acetal by adding water. Some other notes about aldehydes, like just some other reactions that don't really fit into those two acid-base catalyzed categories I was just talking about. There's the Wittig reaction, which again only applies to ketones and aldehydes, not ever carbonyls. The Wittig reaction uses free phenyl groups. Like as the reagent, there's free phenyl groups attached to a phosphorus. And pH for phenyl just stands for a benzene ring. And then the phosphorus is attached to a carbon, has a negative charge, and the carbon can be attached to some more carbons. So these are the conditions for a Wittig reaction. I don't think you have to know the mechanism. Basically, all you have to know is if you see this Wittig reaction with the triphenyl phosphorus reagent, whatever carbon chain you have here attached to the phosphorus, just replace the oxygen with a carbon. You're turning the carbonyl into an alkene. So that's really all you have to know about the Wittig reaction. I think it just turns aldehydes or ketones into alkenes. Okay, and then one last thing about ketones and aldehydes is if you have a carbon-carbon double bond conjugated with the ketone or the aldehyde, and it's conjugated because we have alternating single and double bonds here, this has a resonance form that you can draw like this. You can see in both of these resonance forms that the carbonyl carbon here has a neutral charge, but this carbon here has a positive charge in one of the resonance forms. So this spot is a better electrophile, and the majority of nucleophiles are going to attack that positive charge instead of the carbonyl carbon. The only nucleophile that I think you have to worry about that will still attack the carbonyl carbon is Grignard's. But everything else, so like cyanates, amines, alcohols, like all the other nucleophiles are going to attack the conjugated position where that positive charge is. And in terms of showing a mechanism for that kind of attack, I'll just do it briefly because it can confuse people sometimes. So I'm just going to put Nu for a generic nucleophile. It's going to attack here. Going to have some electron flow. And I'm just going to say, like, we have like some nucleophile, let's just say it has a proton, and we have like acidic conditions or something. So after that first step, you end up with an O-, and you have your nucleophile attached. Now it's a positive charge. So you can transfer that proton to that negative oxygen there. And this isn't something you would have known when you were first learning this during the semester. But this is an enol. It can do tautomerization to go back to a carbonyl. So that's what's going to happen. And if you want to show the electron flow, it basically looks like this. You're just moving the proton to the alkene. And you get the carbonyl back. And you have the nucleophile attached. So like all of those mechanisms would look the same. And if you were adding a Grignard and it was attacking the carbonyl carbon, that would look exactly the same as any other base catalyzed nucleophilic addition. So that's nothing special. Okay, so that's all I'm going to say about ketones and aldehydes. Next is carboxylic acids and their derivatives. I'm gonna go over like the list of the common ones and how you would name them. So, well, just in general, like a carboxylic acid derivative looks something like this. You have a carbonyl, and you have something attached to the carbonyl carbon that can behave as a leaving group. Might not be the best leaving group, but it can be a leaving group. So that's just a general carboxylic acid derivative. If, well, this isn't a carboxylic acid derivative, but if X is an alcohol, basically, this is a carboxylic acid. And like what I'm going to say is probably going to sound obvious, but let's just review. And in terms of naming these, like for example, if you had this structure, you use the oic ending or oic acid ending for naming these. So like this has 4 carbons, so it has but in the name, and it's butanoic acid because it's a carboxylic acid. So like this part, the oic acid came from the fact that it was a carboxylic acid. If the leaving group is basically an ether, like you have an oxygen and you have an alkyl group, this is basically an ether, then this is an ester. And as an example for naming these, the way you name them first is you look at whatever is attached to the oxygen, like here, the singly bonded oxygen, you look at the alkyl group attached to that. Here, it's a methyl group. So we start by saying, like, this is methyl because there's a methyl group there. And then the carbonyl side has free carbons, so that's prop for like propane. And then you put propano-8 because it's an ester. So the O8s just came from the fact that it was an ester. The methyl came from this methyl group attached to the oxygen there. That's just an example. They can get a little more complicated than that, but I doubt you'll have really tricky nomenclature. Just understand the basics of naming these, they'll probably be good enough. If your leaving group is a halogen, either a chlorine or a bromine, although chlorines are much more common, so that's what I'm going to show. This is an acid chloride. Spell. And as an example of naming one of those, this has 5 carbons, so it's going to have pent as part of the name. And then the ending is oil chloride. So this is the parts that came from the functional group, the oil chloride ending. And the pents just came from the 5 carbons. And then the last normal carboxylic acid derivative is an amide. So that's when you have a nitrogen as your leaving group. It's going to be an amide. And naming these can be tricky, but it didn't look like Brooke really covered naming tricky ones, so I think you'll just have to name something like this if you are asked to name one. And naming this structure would just be propamide, so you basically just use the amide ending for the name. It's pretty straightforward. And there's also an oddball in terms of carboxylic acid derivatives. There's nitriles with carbon-nitrogen triple bonds. So if you have a carbon-nitrogen triple bonds, that's nitrile, like I just said. Naming these, there's like 2 different kinds of ways to name them, I guess. So for example, this, it has 4 carbons if you're including the carbon in a nitrile, and you do include it here because there's no other functional groups. So the way you would name this is butane nitrile. I might This might not be spelled perfectly, but that's the general idea. That would probably be good enough. Just use the nitrile ending, kind of like we just used the amide ending for amides. But if you have another functional group in the molecule, so for example, if you have a ketone, then you do not count the nitrile carbon as part of the parent chain. So even though there are 4 carbons here, you don't count that carbon on the right in the nitrile as part of the parent chain. So the parent chain is going to be 3 carbons long. And you're going to call the nitrile as a whole as a substituent, and it's going to be called a cyano group. So this is the numbering for this. The cyano group is on carbon 1, so it's going to be 1 cyano and then 2 propanone because it's a ketone for the parent chain. Like what I'm trying to get at here is like don't count the carbon in the nitrile as part of the parent chain. If there's another functional group, call the nitrile as a whole a cyano. And that can be a little tricky, so just good to be reminded of. Okay. Speaking of nitriles, there are a few reactions that you guys covered with them. In terms of synthesizing them, I covered it earlier when we talked about synthesizing amines, but I'll just cover it again because seeing it multiple times might help it sink in more. They can be made from SN2 reactions with alkyl halides if you use a cyanate. And just as another reminder, I've brought this up before, but like this is an SN2 reaction. And this here is a primary substrate, so it's fine. But if I were to try to form, or I would try to do like the same kind of reaction with a cyanate on this, it wouldn't be an SN2 reaction because this is a tertiary substrate. If you try to do an SN2 reaction on a tertiary substrate, you're much more likely to get an elimination product. So you get an E2 instead of SN2. And if that's what you want, cool. But if you're trying to make a nitrile, that's not what you want. So you want to have a primary or secondary substrate to be able to make a nitrile this way. And another way you can synthesize nitriles is if you are starting with an amide and you react it with SOCl2, that's going to just turn this into a nitrile. So it'll turn it into this. And you don't really have to memorize this if you have open note tests, which I'm assuming both classes do still. But if you want a way to try to remember this quicker so you don't have to search for your notes, this is a dehydration reagent. Not usually what we used it for in this class, but it can also act as a dehydration reagent, which means that you're losing water. There's 2 hydrogens right here, there's an oxygen right here, so that's water right there. If we lose that and we kind of shift some electrons around, you end up with that carbon-nitrogen triple bond in a nitrile, so that kind of helps remember it. If that confuses you more than helps you, just, I guess, write this down and look for it when you need it on a test, but I think this little detail helped me a little bit. So those are ways to synthesize nitriles. There's also reactions you can do with nitriles. If you react a nitrile with a Grignard reagent, you have an acid workup step, like usual. It's not going to give you what you would think it would give you, unless you remember this, but it's going to give you a ketone. So this is a pretty weird reaction, so it's just good to be aware of, because you might get it wrong if you're like asked to complete this reaction, because that's not obvious. Nitrile plus Grignard equals ketone. And I brought this up earlier, but I'm just going to go over it again because it might help. if you reduce a nitrile with LiLH4 and acid, you're going to get an amine. And lastly, if you add water with either an acid or a base catalyst, and it's probably a good idea to heat this as well because nitriles probably aren't very reactive. That's going to turn the nitrile into a carboxylic acid. And this reaction is why nitriles are brought up in this part of the class to begin with, because a carboxylic acid derivative, by definition, is like, if you add water to it, it becomes a carboxylic acid. That's what we just did, so that's why nitrile is a carboxylic acid derivative. I'm going to bring that up one more time, just because in case you have to know the mechanism for that last one I just showed, I'm just going to put like water and H+. It falls through a amide intermediate before it becomes a carboxylic acid derivative, but it usually just goes all the way to a carboxylic acid. Just if you have to show the mechanism for whatever reason, this is an intermediate in amide. And I've gone over it on one of my worksheets if you can't figure out how to do it. But I don't know, if you have time, that might be good to be comfortable with, just in case, for whatever reason it's brought up. Okay, so now we'll talk about carboxylic acids briefly. They're carboxylic acids, they're acids, that's in the name, they're very strong acids. And most nucleophiles, if they're good nucleophiles, they're also good bases. So like this carbonyl carbon is still electrophilic, just like a ketone or an aldehyde's carbonyl carbon is electrophilic. But pretty much all nucleophiles, if you add them to this, they're going to act as a base and are going to take that proton instead of attacking the carbonyl carbon, because acid-base reactions are just usually faster than other reactions. So basically you can't really add nucleophiles here very easily, at least not like negatively charged or basic nucleophiles. And that proton that I just showed getting taken away is pretty acidic, because once you have this base, it has a resonance form with the other oxygen, and the resonance stabilizes the base, so the base is weaker, the acid was stronger. That just explains why carboxylic acids are strong acids. In terms of synthesizing carboxylic acids, I've talked about it a little bit, kind of indirectly. If you have a primary alcohol like this, or if you have an aldehyde, you can start with either of these. And if you oxidize them with a strong oxidizing agent like achromate, CrO3, have an acid with this, or use KMnO4, that's going to oxidize the primary alcohol or the aldehyde to form a carboxylic acid. You can't do this with a secondary alcohol, so it has to be primary if you're trying to make a carboxylic acid. Some other ways to form carboxylic acids: if you have an alkyne, carbon-carbon triple bond, and you cleave it, and it doesn't matter what you use to cleave it, so you could either use ozone, O3, or KMnO4. That's going to cleave this bond, and I'm going to redraw that. That's going to give you two of these because this molecule is symmetric, but it's going to give you two carboxylic acids. It doesn't matter what you use. If you're cleaving an alkyne, it's always going to give you carboxylic acids, unless it's at the end of a chain. Like, I guess just because this is review. If we have this alkyne has this carbon at the end of the chain, so I'm just going to put these like same conditions as on that arrow. You would get a carboxylic acid from the left end, and you would get carbon dioxide from that carbon. That's probably not going to be super important for your final, but just in case. Cleavage of alkynes. If it's a terminal alkyne, you're going to get a carbon dioxide as a product. And somewhat related, if you cleave a alkene, carbon-carbon double bond, this time what you use to cleave it matters, so you have to use KMnO4 if you want a carboxylic acid. So if you use KMnO4 on this, then you're going to get 2 copies of this because it's symmetric. You're going to get 2 carboxylic acids. And if you used ozone on this, you would get 2 aldehydes, which is, if that's what you wanted, then that's what you get. But if you're trying to make carboxylic acids, then use KMnO4. Yet another way to make carboxylic acids is through Grignard reagents. So if you're starting with an alkyl halide, in order to make a Grignard reagent, you have to react the alkyl halide with magnesium and an ether solvent, usually THF. And once you have a Grignard, you add carbon dioxide, and in the last step, you add acid. So I'll go ahead and show this. This is the intermediate after the first step, the Grignard. You're adding carbon dioxide, which is just this. Hopefully everybody knows that. It's basically like, it's a carbon with 2 carbonyls because there's 2 carbon-oxygen double bonds. Just like a Grignard adding to a ketone or an aldehyde, like that would be like a nucleophilic addition reaction. This is going to do the same kind of thing. The nucleophile is just going to attack the carbonyl carbon like this. And then you end up with an O-. That's what the last step is for with the acid, just to protonate that. So you end up with a carboxylic acid if you do a Grignard plus a carbon dioxide. And when you do that, you're adding 1 carbon in the process because there's a carbon and carbon dioxide. So that's an important detail. Okay, and one last, or like another way to form carboxylic acids. I'm kind of going to group these together. If you have a nitrile or an ester or an acid chloride or any other carboxylic acid derivative, literally all of them are going to react the same way. If you add water with either an acid or a base catalyst, they're going to turn into a carboxylic acid because they're carboxylic acid derivatives. They're all going to react the same way. So that's just another way to synthesize carboxylic acids. And last, I brought this up earlier with the aromatic reactions, but I'll just go over it again. And I also didn't go over this detail back then. But like, as long as you have a benzoic hydrogen like this, and you react this with KMnO4, it's basically going to cleave the rest of the alkyl chain and just form a benzoic acid, which is a carboxylic acid, and that's what we're talking about right now, so it's kind of relevant at the moment. That's just another way to form a carboxylic acid. Okay, so there is some reactivity that comes with the various carboxylic acid derivatives. And the trend for the reactivity is basically the reverse of what we saw for the electrophilic aromatic substitution reactions with benzene rings. So like with electrophilic aromatic substitution, benzene was the nucleophile because one of these double bonds was attacking an electrophile. So stuff that sped up this reaction was like, I guess like to speed it up, you want to donate electrons to the benzene ring. So you had electron donating groups like alcohols with their lone pairs, they donated electrons with their resonance forms, like I showed. So just electron donating groups speed up this reaction because benzene is the nucleophile. But most of the reactions, well, what we're looking at this semester with carboxylic acid derivatives, they're nucleophilic acyl substitutions. So like you're starting with one carboxylic acid derivative, you're adding some sort of nucleophile, and you're basically just substituting the leaving group, this X, with a nucleophile. I'll show a mechanism for that, but this is just like generally what a nucleophilic acyl substitution reaction would kind of look like. In here, this isn't the nucleophile like it is with benzene. This is the electrophile because it's the carbonyl carbon that's acting as the electrophile. So if we want to speed up a reaction with carboxylic acid derivatives, then we want to withdraw electrons because we want to make that carbonyl carbon a better electrophile, so then it's more reactive and it can react faster. So like the trend is going to be the reverse of what we saw with the benzene rings and those reactions. And that might be confusing, but it's just because with benzene it was nucleophile, with the carbonyls it's the electrophile. Okay, so like I can show what I mean by like all this donating an electron and withdrawing electron business. Like chlorines, they were weakly deactivating with benzene rings because they withdraw electrons because of induction. They're still doing that here. They withdraw electrons by pulling electrons away from the carbonyl carbon. And by doing this, by withdrawing electrons from carbon, it's a better electrophile, so faster reaction. So like, even though chlorine was a deactivator for benzene rings, it's a very strong activator for this reaction with carboxylic acid derivatives because we're making this a better electrophile. And then if we look at the other extreme with amides, these amines were the strongest activators with benzene rings because they have a lone pair, they donate through resonance. They donate electrons, which made the benzene ring more nucleophilic. It made the reaction faster. But here, by donating electrons for resonance like this, they're donating electrons to that carbonyl carbon. So they're making that carbonyl carbon less electrophilic. So the reaction would go slower because a nucleophile would have a harder time attacking it. So these were two kind of extremes on the benzene ring, and they have reverse effects than they did with benzene. And this is why. So in terms of like a chart, if you want to have one or see one again, because it is good to be aware of the reactivities. Like you should be able to explain potentially like why one thing is more reactive than the other, and resonance and induction are ways you can explain that. But if you just want a chart to refer to quickly, acid chlorides are the most reactive carboxylic acid derivative. Oh, I actually forgot to bring these up, but I guess I'll go for naming them now since I brought it up. This is an acid anhydride. It's the second most reactive carboxylic acid derivative, followed by esters, and then last is amides. Carboxylic acids are just about as reactive as esters are, but you can form all of these from a carboxylic acid. But what you can't do is like you can't go straight from an amide to a acid anhydride because an acid anhydride is more reactive than an amide, and you can't really go from a less reactive to a more reactive thing. That's just not very likely to happen. You're not going to get much product. So, but like I just said, you can turn any of these into a carboxylic acid. So if you wanted to form an acid anhydride from an amide, you would turn the amide into a carboxylic acid, and then you could turn the carboxylic acid into an acid anhydride, and that would work fine. So that's why being aware of like the relative reactivities of these is good, because if you're given like a synthesis question and you're making a more reactive thing from a less reactive thing, you're going to have to go through a carboxylic acid as an intermediate, or it's not really going to work. And like I just said, I forgot to bring up acid anhydrides in terms of naming them. Actually, I honestly don't think they're going to have to. If you're worried about that, it's in lecture notes somewhere probably. I just don't think it's likely. So now, like I said, these reactions that I've just been talking about, like reactivity for, they're nucleophilic acyl substitution. And there's two general mechanisms for this, just like there are two general mechanisms for the nucleophilic addition reaction with ketones and aldehydes. There's a base catalyzed and an acid catalyzed. I'll show the base catalyzed first. That would be if you have a relatively strong nucleophile with a negative charge as your nucleophile. The way that starts is the nucleophile attacks the carbonyl carbon. And that pushes the carbonyl bond up towards the oxygen. Get an O-. And your nucleophile is attached, and then you reform the carbonyl. You don't kick out the nucleophile, you kick out the leaving group. You basically just replaced the leaving group with a nucleophile. This is the base catalyzed mechanism. And pretty much all of them are going to look exactly like this. There's one minor deviation that I'm going to go over, but they all follow the same general steps. Nucleophile attacks, carbonyl reforms, kicks out the leaving group, and you're done. It's really short and simple. And the acid catalyzed mechanism also always follows the same pattern. So there, you're probably going to have a weaker nucleophile, might have a proton on it, and you have acidic conditions. The first step for this is going to be the same as it was with acid catalyzed stuff with ketones and aldehydes. So you're going to protonate the carbonyl oxygen. You form a cation on the carbonyl carbon. That's a better it's a better electrophile. So now the weak nucleophile can attack that carbon. Now the nucleophile we just added has a positive charge. The leaving group is always going to have at least one lone pair. So what happens at this point generally would be a proton transfer. I'm going to go ahead and erase this. That should be fine. So now the nucleophile has a neutral charge. The leaving group has a proton. We can reform the carbonyl and kick out the leaving group. And then the last step would just be taking the proton from the carbonyl oxygen. It's basically just going to pop off because it's in an acidic solution. And this, again, is acid catalyzed mechanism for nucleophilic addition, or nucleophilic acyl substitution. Okay. So they're always going to look very similar to this, no matter what the nucleophile is. If it's acidic conditions, it's going to follow these same steps. The only difference is, what is this leaving group? and what is this nucleophile, but it's always going to look like that. So it's kind of like plugging something into a recipe. You just have to recognize what the differences are. But again, same thing every time. Now, in terms of that deviation I was referring to, that would be if you are starting with an ester. So the OR is your leaving group, and you're adding hydroxide as your nucleophile. So this is base catalyzed because the nucleophile has a negative charge. The first step is just nucleophilic attack. And then the second step, the carbonyl reforms, we kick out the leaving group. And at this point, what we have is a carboxylic acid. But what we just kicked out, this is an alkoxide. And this is a very strong base, and a carboxylic acid is a strong acid. So there's going to be one final step where the base takes the proton from the carboxylic acid. And these first two steps were reversible, that's why I drew this equilibrium arrow. But this last step basically isn't reversible, so you'd have to add a proton with an acid in some second step if you wanted a carboxylic acid at the end. If not, you're going to be stuck with a carboxylate. And this is just one extra step. It's the same first two steps, nucleophilic attack and then carbonyl reforming. So the only reason I say this is a deviation is because the leaving group you kicked out is a very strong base. So it does that extra step, but other than that, it's the same mechanism. Okay. So at this point, I'm not going to be showing all of the mechanisms because they fall under those two categories I just showed. I can point out like what kind of mechanism they're following, and you can practice showing them if you like, but it's the same as I just showed. So the most reactive acid derivative is a acid chloride, and they can basically do anything. Like they can form any of the other carboxylic acid derivatives, or they can form a carboxylic acid. So like if you add water to these, you get a carboxylic acid. If you add an alcohol to them, you will get a ester. If you add an amine to them, you'll get an amide. And if you add a carboxylate, looks like this, it's deprotonated carboxylic acid, you'll get an acid anhydride. And in all of these, if you showed a mechanism, like the leaving group here is a chlorine, so the chlorine, when it gets kicked out, it's going to get kicked out as a Cl minus. And that's like, if it ends up getting protonated by something, then you're going to form HCl. And there's probably going to be protons. Like if you're adding water, there's going to be protons. If you're adding an alcohol, there's going to be protons. So like, it's likely that the chlorine will get protonated. This is a strong acid. It can do acid catalysis, and it can cause extra reactions to happen that you might not want. So if you're doing something with an acid chloride, you're doing one of these reactions, you usually also have some sort of base along with the nucleophile. And the base, pretty commonly, is either triethylamine, which is this because there's free ethyl groups on a nitrogen, that's a base, or pyridine, which is basically a benzene ring with a nitrogen for one of the carbons. So these are two common bases that you use to basically stop HCl from reacting so you don't get side reactions. And I'm not going to redraw all these reactions with an acid anhydride, but basically an acid anhydride can do all of these reactions, except for this last one because it's already an acid anhydride. But it's just about as reactive. It's going to do the same kinds of things. And acid chlorides and acid anhydrides are both very reactive because they're the most reactive ones. And they all pretty much always are going to do base catalyzed mechanisms. Even if the nucleophile you're adding is weak, like water or an alcohol, that's not a very good nucleophile, but it can still just straight up attack the carbonyl carbon. It doesn't need an acid to protonate it first, just because it's so reactive. So that's good to know. Both anhydrides and acid chlorides are going to always do this mechanism, regardless of the nucleophile. Okay. And then in terms of the rest of the carboxylic acid derivatives, they all have kind of similar reactivities. And I'm just going to kind of start listing some general reactions, sort of refresh your memory. If you want to form an amide from a carboxylic acid, you would want to add an amine and then use DCC. That's basically like a catalyst to get the reaction going. This only is necessary if you're trying to form an amide from a carboxylic acid. You can also form an ester from a carboxylic acid with an alcohol and acid. That'll form an ester. And I didn't draw these as reversible, but I should have, because they are. The reactions with acid chlorides and acid anhydrides aren't really reversible because the acid chlorides and acid anhydrides are so reactive you can't really go back. But these are, so you can go back and forth between them. It just depends on what you add to them. So these are just some things you can do with carboxylic acids. And you can also form amides from esters the same way, just add an amine to an ester, and actually you'd use an acid catalyst with that, but just it's a similar kind of thing. And if you add a Grignard to a ester like this, that's going to pass through and this is also base catalyzed in terms of the mechanism, but that's going to pass through a ketone as an intermediate, because if you showed a mechanism like the nucleophile attacks and then you kick out the leaving group after you form the carbonyl, so you end up with a ketone because you've attached one Grignard. But a ketone is more reactive than a ester. So the thing we just formed is more reactive than what we started with. It's going to react with another Grignard, and we are going to end up with a tertiary alcohol. And there's not really a way to stop that. Similarly, if you add LiAlH4, the hydride reducing agent that works on esters, an intermediate you're going to get after you add one hydrogen is going to be an aldehyde. But again, an aldehyde is more reactive than the ester, so this is going to react further, and you're going to end up with a primary alcohol. And these reactions are not reversible because Grignards and hydrides are very strong nucleophiles, so you can't really go backwards to reform them because they're so reactive. So irreversible is strong nucleophile, very strong nucleophile. Some other reactions, and like I've said before, I'm not going over literally everything. I'm just trying to go over some of the important things. And this is a bit of a weird case, even though like it's something that got brought up before. I'm just going to put these two side by side so you can see the difference. If you react a carboxylic acid with SoCl2, that's going to turn it into an acid chloride. If you react an amide with SoCl2, it's not going to give you an acid chloride, that's going to give you a nitrile. So very, very different, even though it's using the same reagent and they're both carboxylic acids or carboxylic acid derivatives. So this might be good to be aware of that drastic distinction. It's kind of important. So yeah, just those are some carboxylic acid derivative reactions that would be good to be aware of. And yeah. One last thing, I guess. Obviously, you can form esters from carboxylic acids, like I showed. You just add an alcohol to a carboxylic acid, and you get an ester. But you can also turn one ester into another ester, and that's perfectly reasonable. And you would do that the same way you would form an ester from a carboxylic acid. So I'm going to put a prime here on this R group just to show that it's a different alcohol. And this is just transesterification. You're turning one ester into another. That's just like, you might not think that wouldn't be possible, but it is a thing you can do. So just good to be aware of. Okay, so now I'm going to talk about like enols and enolates in general, those reactions alpha to carbonyls and such. Even without a catalyst present, whenever you have a carbonyl, there's some sort of equilibrium that it has with its enol form, which looks like this. And as I showed with these arrows, the equilibrium favors the carbonyl, but it's still an equilibrium, and you can add catalysts to make it favor the enol more. You can't really make it completely transfer to the enol, but as long as you can form some, then you can use the enol to do stuff. So you can do that with either an acid or a base catalyst. And I'm just going to bring this up because it's something that might confuse some people. If you add an acid catalyst to a ketone, you can make it form an enol, like I just said. So this is one thing that you can do if you're adding acid. Or you can also form a gemdiol, like we talked about earlier. Because if you add water with, or okay, I guess I should put H3O plus specifically. But if you add water with an acid catalyst to a ketone or an aldehyde, you can form a gemdiol somewhat. However, a gemdiol is a thing that could form, and it would be in a bit of an equilibrium, but it's not really reactive, like at all. It doesn't really do anything. But an enol, as you know, and I'm going to talk about, is reactive because the alpha carbon can act as a nucleophile. So as long as you have a little bit of this forming, it can do reactions, and then that will lead to a product. Whereas this will be forming, but it doesn't react with anything, so you can basically pretend it doesn't exist because of that. So if you're adding an acid catalyst and nothing else, you're probably going to be forming an enol, and then the enol will be reacting with something else. Okay. There's a mechanism for how acids and bases catalyze the formation of enols and enolates. It might be good to be comfortable with. So for the acid catalysis, it's going to follow the same first step that acid catalysis always does. You're going to protonate the carbonyl oxygen, because that's the only acidic or only basic thing in the molecule. that puts a positive charge here. And at this point, you have a proton alpha to the alcohol. There should be 2 here. We formed water when we took a proton from it to protonate the carbonyl. The water can act as a base, and it basically does an elimination step to sort of form a carbon-carbon double bond, and then you get your enol. So that's acid catalyzed tautomerization. You can also do this with a base by a slightly different mechanism. So if you're adding a base like hydroxide, it's going to take the only acidic thing in the molecule, which is the alpha proton. And in case you don't remember, I'll say why that's acidic very shortly. It's because when you take that proton, you form an enolate, and then the enolate has a resonance form with the carbonyl. Resonance makes the base stable, so it's weaker, so the acid is stronger, and this proton is acidic. And then at this point, this could get protonated by the water we formed when the hydroxide took a base, and that would reform the hydroxide, so you have a base catalyst. And that's a way to form an enol with a base catalyst. But this part here, as you know, is an enolate, and enolates are more reactive than enols. That's probably going to be the reactive thing that we're considering. But it can go to an enol if it doesn't have anything to react with. So these are the mechanisms, acid and base catalyzed. Okay, so yeah, that's that. And what can you do with an enol? Basically, only one thing with an enol in particular. It's alpha halogenation. That's all you guys really covered this semester. So like if you add acid and then you add something like Cl2, that is going to give you a chlorine alpha to the ketone. And it does that by passing through the enol intermediates, and it forms that enol by the mechanism I just showed, the acid catalyzed one. And then this carbon is nucleophilic, so we have a nucleophile, a Cl2 or Br2 or an I2. These are all electrophiles, so the nucleophile can attack the electrophile. And then the carbonyl can reform, and you can do some proton transfers. I don't want to show the whole thing, but like just basically this would reform, and then you would lose this proton, and you would have that product that I have shown. But in the end, you have alpha substitution. And that's pretty much all an enol can do, just as far as you know, at least just alpha halogenation. So something I want to point out, well, I still have this here. I just said Cl2 is an electrophile. So so when we added the acid, it's there to form an enol. But if we instead have acid and then a nucleophile, like an alcohol, then the purpose of the acid is just to make this carbonyl carbon a better electrophile so the nucleophile can attack. So then, I'm gonna put like a dividing line. Then the reactive species isn't this enol like I have drawn here. It's gonna be this intermediate where you have the carbocation below the alcohol, because then the nucleophile can attack there. And that is just because like we're reacting the ketone with a nucleophile instead of an electrophile like with the halogen. So what I'm trying to get at here is like, you can do two different things with an acid catalyst with a ketone or an aldehyde. You could form an enol, or you could just stop at something like this, and then that's your reactive species. And what it reacts, like which part is reactive, depends on what you're adding to it. Like I just said, enol will react with an electrophile. If you have a nucleophile, it's going to be a carbocation. So it's just good to look at what you're adding to things and determine if it's a nucleophile or an electrophile. And some things you can do with alpha halogenation through enols, just as a sort of refresher. Also, if you're adding acid and you're adding a halogen, you're going to do it through an enol, like I've been saying. And the enol that's going to form is the more substituted one. So like with this, we could either form this enol or this enol. And the more stable alkene is going to be the one that forms for enols always. So it's going to be this one because it's the more substituted one. So because that's the more substituted side, this is going to be where the halogen ends up going. And then once you have a halogen alpha to a carbonyl, you can do a few things with it. You could do like some sort of SN2 reaction by adding a nucleophile. And then depending on what that nucleophile is, you could do more stuff to that. Or you could add a base like pyridine. I guess I'll just draw the structure. That'll probably be easier. But you have a base like pyridine, and that can do an E2 reaction to form a conjugated carbon-carbon double bond, and then you can do more stuff with that, like conjugate addition or Michael addition, as we'll see. Like, there's a lot of things you can do once you add a halogen alpha to a carbonyl. So it's a pretty important step in some synthesis problems, and that's why like you might want to just be really comfortable with this idea. Like, that's probably going to come up at least once, because then it can lead to a lot of possibilities. Okay. So if you are trying to do alpha halogenation and you only want to add one halogen, it's usually a better idea to do acid conditions, so you form an enol. Because the way it does this is like, it does the acid catalyzed mechanism, like I've shown. And once you have this chlorine here, it has, like, it pulls electrons away from, or towards it inductively. So it's going to pull, like, electrons from the entire molecule towards it. And by doing that, it makes this oxygen less basic. So because of that, like, it's harder to protonate that oxygen again, so you can form another enol, so you can add another halogen because it's less basic. So the product you form is less reactive than what you started with, and you're basically going to only add one halogen because of all of that. But if you do the same reaction with basic conditions, so you're forming enolates, that's Cl2, not C12. If you're going to get the same product, you're going to get the alpha halogen. But again, it's pulling electrons, except like this time we're forming enolates, so we're taking these alpha protons to make enolates, and then that's reacting with halogens. By pulling electrons away from these, if you draw the enolates, didn't want to erase all of that, but if you draw the enolates, by pulling electrons away from the negative charge, we stabilize it, so we make the base weaker, so the acid was stronger. So basically, as halogens add, it becomes more reactive. So we can't really stop after adding just one halogen. It keeps going. So after the first halogen, you're going to form another enolate that's going to react with another chlorine. And then it's even more acidic because of that same reasoning. So we're going to form another enolate, and that's going to react with another Cl2. And you end up with free chlorines replacing all of the hydrogens alpha to the ketone. And at this point, this looks kind of like a carboxylic acid derivative. And it can react like one because we have hydroxide that's still a nucleophile. I'm going to go ahead and erase this. So this is just a base catalyzed nucleophilic acyl substitution at this last few steps. We added the nucleophile, the OH-, reform the carbonyl and kick out the leaving group. Get a carboxylic acid and the leaving group that just left. And then that has a negative charge, so it can take that proton. And you end up with a carboxylate and chloroform. And this can happen with Br2 or I2 as well. And these last few steps, like with the hydroxide adding and kicking this out, this only happens if you have a methyl group next to a ketone. So if we had something like this, there's no methyl groups alpha to the ketone, so it wouldn't go that far. It might replace all of the alpha hydrogens with halogens, but it wouldn't do this last step here. Also, if you're doing this with I2, you would end up forming CHI3 if there's a methyl group next to the ketone. And as I've said before, this is a yellow precipitate. And it's only going to form if there's a methyl group alpha to the ketone. So like that's a conceptual question you might be asked that might be good to be aware of. That's going to form if you add I2 with basic conditions to a methyl ketone. Okay. And some other things enolates can do are alpha alkyl substitutions. So like if you have a ketone and you add a base like sodium hydride, and then you add an alkyl halide like RCl. So the first step is going to form an enolate through the base catalyzed mechanism I showed before. Once you have an enolate, that's a nucleophile, an alkyl halide is an electrophile. So this is going to do an SN2 step. And that's just going to add a carbon chain alpha to the ketone. And this, as far as I know, it really only works with primary alkyl halides. Because in enolates, like, it's this whole thing that's the nucleophile. It's very bulky, so elimination reactions are more likely if you use it with a secondary substrate. So that's good to know. This is just alpha alkylation. And we've been talking about forming enols and enolates with carbonyls like ketones and aldehydes. But you can also form them with nitriles, because if you have an enolate next to a nitrile, that's also resonance stabilized, just like it is if it's next to a ketone. Or if it is next to a nitro group, because that's also resonance stabilized. That stabilizes the base, makes it weaker, so the acid was stronger, so you can take it. Or with esters or other carboxylic acid derivatives, just like all of these have resonance stabilization, so you can form enolates with them. Okay. So one thing is if you want to do alpha anything with a carboxylic acid, it's like say you want to do that reaction I was just showing, forming an enolate at the alpha position and then reacting that with an alkyl halide, well, you would add a base like sodium hydride, and then you would add an alkyl halide. But the problem is, like, that's a base, this is an acid, so you're not going to get this enolates. Instead, you're going to form a carboxylate, you're going to deprotonate the carboxylic acid. So you can't really do alpha, well, you can't do it the same way you do it with the other stuff. You can't do alpha substitutions through enolates or through enols as easily. There is one way to do alpha substitution with carboxylic acids, though. I'm not going to go over the details of this, but I've talked about it before. But if you react a carboxylic acid with PBr3 and Br2, that's PBr3. I'm sorry, that was drawn poorly, but that's PBr3. So if you react it with PBr3 and Br2, and you react it with water in a second step, that just adds a bromine to the alpha position. And I haven't said it yet, which is my bad, but alpha is just like the spot next to the carboxylic acid or whatever else you're interested in. That's all alpha means. Okay, I don't know, the last things you guys covered in this part of the course was acetoacetic ester synthesis. So here, you add a base, and the base should match your ester. And I'll explain why in a second. But the base matches the ester, you add an alkyl halide, and then you add H3O plus, and you heat it. This spot that's alpha to both of the carbonyls has the most acidic protons, so that's where the base is going to form an enolates. That's what the first step does. The second step is an SN2 step, where the enolate attacks the alkyl halide. So then an intermediate after the first two steps would be this, where you've put an R group here. Now H3O plus is going to turn the ester into a carboxylic acid because you're adding water with an acid catalyst. It's not really going to do anything important to the ketone. And now we have a carboxylic acid and its beta to a ketone. If you ever have a carboxylic acid beta to any other carbonyl and you heat it, then you're just going to lose the carboxylic acid as a whole. And it doesn't matter what the context is, so it's going to come up here, and I'm going to talk about it again later, but anytime this comes up, that's going to happen. This is, like I said, acetoacetic ester synthesis. I'm not spelling it correctly, but it's acetoacetic ester synthesis. And the product is always going to be acetone. That's what this is, with an alkyl group substituted at the alpha position if it's acetoacetic ester synthesis. A similar reaction where I'm not going to show all the intermediates. Instead of having a ketone beta to an ester, you just have two esters beta to each other. And if we do the same conditions, we use a base that matches the ester in the first step. We react it with an alkyl halide in the second step, and we add acid and heat in the last step. Like the last step is going to turn both of the esters into carboxylic acids, and then you're going to lose one of the esters, or one of the carboxylic acids, because you're heating it. So the product you end up with is a carboxylic acid with an alkyl group at the alpha position. Always. And this is malonic ester synthesis. Okay. You can also use a secondary amine with either a ketone or an aldehyde to form an enamine. That's something we talked about earlier. And when you do this, like this is a secondary amine, like I said, and you have an aldehyde, so you're going to form an enamine. An enamine has a resonance form you can draw like this, which enols don't really have much, if any of, but enamines do. And when you do this, you put a negative charge on the alpha position to the nitrogen. So an enamine is basically enolate, and it can do all of the reactions that an enolate can do. So anything we've seen earlier, or all of the enolate reactions I'm going to talk about later, an enamine can do them. So this is just Stork enamine synthesis using an enamine as an enolate, basically. And once you've used the enamine to act as a nucleophile and add to whatever else you're interested in, you would just, it's like, I'll just put like Rx so we can do like alkylation. That's one step. And then if you add water to an enamine, that will reverse the reaction and give you the aldehyde back. So you would end up with this product here because the Rx, like the enolate or the enamine, just did this reaction, this SN2 step, and then the water just reversed the enamine reaction and gave you the aldehyde back. Okay. In terms of like the importance of matching your base tier ester, if you have like a methyl ester, do you react it with NaOCH3? This could act as a nucleophile and attack the carbonyl carbon. To do like a nucleophilic acyl substitution. But both of these things are the same, so when the carbonyl reforms, it doesn't matter which one kicks out. Okay, so yeah, when you kick out one of these, you're gonna end up with the same thing you started with. You're gonna end up with the same ester because your base matches your ester, so it doesn't matter. If I instead used an ethyl base, like an F oxide instead of a methoxide, this could also do that nucleophilic attack. Kick out the leaving group, which is the methyl part, you're going to end up with an ethyl ester. So it's a different ester, but you could still form an enolate here at the alpha position, so you haven't completely ruined the reaction. If you're trying to form an enolate, you consumed a bit of your base to do this reaction instead. But again, like using a base that matches your ester is a good idea. However, if you use like a methyl ester again, and you add sodium hydroxide as your base to try to form an enolate, it's going to follow the same mechanism. So like nucleophile attacks, this isn't the mechanism, I'm just summarizing it, but you end up like kicking out the leaving group and not quite like that. So you kick out the leaving group, you replace it with the nucleophile. But this leaving group is a strong base. We just formed a carboxylic acid that's a strong acid. you end up with a carboxylate. And that's kind of irreversible. You're stuck with that. You can't really form an enolate anymore. So adding a hydroxide to an ester will mess it up and you won't be able to form an enolate. So that's why it's important to match your ester to your base, so you avoid competing reactions like this. Okay, and now last thing with this section of the course, kinetic versus thermodynamic enolates. So enols, like I said before, if you're using an acid to do these alpha substitutions, then you're going to form an enol. And the enol is always going to be the more stable one. So in this case, it's going to be this one on the right, because that's where the more stable alkene would form. That's where the halogen is going to end up. But if you're using a base to form an enolate, it depends on what conditions you use to determine like which enolate you're going to form. So, no. Going back to that same ketone, you could either form, and I'm going to draw this as alkenes actually, but you could either form this alkene and that, and like that enolate form, if you draw the resonance form, or this alkene. The one on the bottom is more stable because it's more substituted. The more stable product is the thermodynamic enolate. And then the less stable one is the kinetic enolate. It's called kinetic because it forms faster, because it's easier to form the enolate here since there's more protons there and it's less sterically hindered. The way the two teachers approach making these different things is different, which is kind of annoying, but it's just, it is what it is. For Samako, he uses sodium hydride in 25 degrees Celsius. And for Brooke, he says to use 0.9 equivalents, yeah, and negative 78 degrees Celsius. I'm pretty sure I got it correct this time, even though I usually mess it up during workshop. And then to form the kinetic enolates, you would want to use LDA and negative 78 degrees Celsius for Samako, and then 1.1 equivalents LDA. And then depending on which enolate you formed, that's where you would add stuff, like adding electrophiles. I don't think I'm going to cover polymers and proteins just because you guys very recently covered that. So I'm just going to cover aldols and glycine and like those reactions, and then I'm going to stop. I'm still going to have the review session. So if you want to ask me about proteins and stuff, like you can ask me there, but I've been doing this for almost 3 hours. So I'm just going to stop after this chapter. Okay, so now we're on to like aldols and glycines and stuff. So in these, you're basically reacting two aldehydes or two ketones together using like a base. Typical product, like if these two reacted together, and I will show the mechanism, but if these two reacted together, this is the product you would get. It's called aldol because you have an aldehyde and you have an alcohol. So like al for aldehyde, and then the OL for alcohol. That's why it's called aldol. And come on. The alcohol is beta to the aldehyde. And it's always going to look like this for an aldol product. It's always going to have the alcohol beta to the aldehyde or the ketone. And this can also keep going to form another product which again, I'll show how it forms. You can form this product with a carbon-carbon double bond on the alpha and beta positions to the aldehyde or the ketone. So that first one of the alcohol is the aldol product, and then this is called the condensation product because you lose water in the process of making that carbon-carbon double bond. Okay, so now the mechanism for aldol. It uses an enolate as a nucleophile. So what you got to do is you got to make an enolate. We have basic conditions. We're just going to say we're using hydroxide. So hydroxide's going to take the proton alpha to the ketone or the aldehyde, whatever you're looking at. It's going to form an enolate alpha there. And then that enolate is a nucleophile. And all we're doing here is we're doing a nucleophilic addition reaction. It's the same base catalyzed mechanism we did with like ketones and aldehydes before and earlier in the class. It's just the enolate is the nucleophile, but it's the same exact base catalyzed mechanism. So the nucleophile attacks the carbonyl carbon. We form this bond alpha to the aldehyde, and I should have drawn the electrophile as red, but I kind of neglected to. But this is the electrophile in red. And in a second step, it's going to get protonated by the OH minus, or by the water that formed when the hydroxide took a proton. And that's going to give you your aldol product with the alcohol beta to the ketone or aldehyde. And then this can keep going to form that carbon-carbon double bond. And it does that. We just reformed the hydroxide here, so it was a base catalyst. We can use it to do something else. It can form another enolate, because there's still a proton there. And the enolate will still be resonance stabilized by the aldehyde. And then the enolate can basically do an elimination reaction to kick out the alcohol. This only happens with the alcohol being a leaving group because it's going to form a conjugated carbon-carbon double bond. There's no other cases where an alcohol can just be kicked out like that. But it can happen here, so you can get the condensation product. And we lost a hydrogen here and an OH here, so we lost water in the process. That's why it's called condensation. Okay, so you can react two aldehydes or ketones together, like I showed with those last two examples. You could also try to react two different things together. Like say, I have this aldehyde, and I want to do an aldol reaction, like maybe I want this one to form the enolates and the other one to act as the electrophile. But there's not really a way to force that to happen. So if you were to try to react these two together, like you would run into a bit of an issue. You would end up getting 4 products, which I'll go ahead and show. And I'm not going to explain like where each of these come from. I'm just going to draw them all. If you want to practice like trying to figure out where did each of these come from, like which one was the nucleophile and which one was the electrophile, that might be good practice. But for the sake of time, because it would take a while to explain each one, I'm just going to draw them. All of these should look like typical aldol products. If you look at where the alcohol is in relation to the aldehyde, they should be beta to each other. So that's just something to pay attention to. So yeah, you're gonna get 4 products from this mixed aldol. And then you wouldn't really be able to separate these. That's an issue, because then you're not gonna be able to get the product you wanted. So if you're trying to do an aldol reaction between two different aldehydes, or like an aldehyde and a ketone or something, what you generally do is you have one of your aldehydes be, like, it has no alpha protons. So like this benzaldehyde, this is the alpha position. There's no protons there. We can't form an enolate. So all this could act as an electrophile. So this would be an acceptor. And then you could react it with something else that could form an enolate, say a ketone, like this. That's supposed to be sodium hydroxide. Then, just to show how this reaction would go, this is the bond forming alpha to the ketone. Get an alcohol here in the benzene ring. And then you would also get the condensation product, but that's the aldol product you get. So if you're trying to react two different things together for an aldol, it's better to have one of them have no alpha protons. So like a benzene ring, or you could have a tert-butyl group next to an aldehyde, or literally anything else that has no alpha protons would work fine. And that's all I'm going to say about aldol. Now I'm going to talk about Claisen, and Claisen is very similar to aldol. The only real difference is, like, instead of an enolate attacking an aldehyde or a ketone, it's an enolate attacking an ester. But other than that, like, it's similar because the mechanism is a nucleophilic acyl substitution, and the way the product comes out looks kind of similar to an aldol. Okay, so one difference, and I'll explain this when I go over the mechanism, but it has an acid workup step, which you do not have for aldol reactions. But if these two esters reacted with each other through a Claisen reaction, you would get this product. And a typical Claisen product between two esters is a beta ketoester. You have an ester, alpha is the spot next to the ester, beta is the spot 2 carbons away from the ester. There's a ketone there. So this is just a typical Claisen product. Just like having an alcohol beta to the aldehyde was typical for an aldol reaction. Okay, so now I'll show the mechanism for this. It starts the same way, just base takes proton to form enolate. It's going to take this one. So we're going to form that enolate alpha to the ester. This time we'll do the color coding. We have another ester. The enolate's going to attack the carbonyl carbon, like so. Going to form the bond, the green one, alpha to the ester that acted as the nucleophile. Carbonyl is going to reform, and you are going to kick out the leaving group. And what you end up with is this. And this looks like our product because this is what our product was. But the problem is what we just kicked out, that OR minus, this is an alkoxide. It's a strong base. This beta keto ester, as long as there's still an alpha proton here, which there is in this case because there's still protons there, these are very acidic because they're alpha to 2 carbonyls. So the strong base we just formed is going to take that proton, and we're going to form an enolate. it's not really good to stop with a negative charge on your products. That's why you have the second step as the acid workup. So Claisen requires a secondary, like a second step for acid workup, but the other condensation reactions don't require that. So if you have an ester and you have a base that matches your ester, and then you have a second step where you're adding acid, that second step is a pretty good indication that you're doing Claisen. I think that might be good to consider. Because usually if you have acid workup, like you're either doing it to protonate like an O- to form an alcohol, or it's like here, where you're doing a Claisen reaction and you're protonating that enolates that you don't want to get stuck with here. So just might be good to be on the lookout for. Just like mixed aldol reactions aren't ideal because you can get a mixture of products, it's the same thing with mixed Claisen reactions. So to make mixed Claisen reactions more favorable, you do the same kinds of things, like you want to have one ester have no alpha protons, so then they can't form an enolate. And then it can react with something that can form an enolate, and you're going to get less of a mixture of products. It's like if I reacted that ester on the left that has no protons here with the one on the bottom of the arrow, I would end up with this product. Also, this is all the first step. You would still want to do the acid workup. So just again, having something that can act as an acceptor because it has no alpha protons is good for mixed Claisen. This could also have happened with aldol, I just didn't bring it up back then, but and I also explained like you can form enolates with nitro groups because they're resonance stabilized. Same thing with nitriles. Like you have this resonance stabilization. So because of that resonance stabilization, you can form an enolate like this, and an enolate can react with a ester to do like another kind of mixed Claisen reaction. So you don't have to have two esters reacting with each other when you're doing Claisen reactions, basically. It's only called Claisen if it's between two esters, but it's the same exact kind of mechanism, even if it's not two esters. It's just enolate attacking ester, and then you reform the carbonyl, and you end up with a ketone. So a typical Claisen product, like I've said, has a beta keto ester. This isn't a beta keto ester, but we do have a ketone, and it's beta to another functional group. In this case, it's a nitro group. If we used a nitrile, it would be beta to a nitrile. Like if we used a nitrile to form an enolate like this, then we would get a ketone beta to a nitrile. If we use the ketone, we'd have two ketones beta to each other. So like it doesn't matter. Just like if you have an enolate attacking an ester, the final product is going to have a ketone beta. It's whatever you used to form the enolate. I could go over a bunch of different examples, but like they're all going to look something like this, just with different functional groups. Okay. One last thing about Claisen reactions. I'll take this ester as an example. So here we're still doing the acid workup, but there's something special about the acid workup we're doing here. So I'll draw the Claisen product we're going to get from this. We're going to form an enolate here, and it's going to attack another copy of this ester. And we're going to end up with that typical beta keto ester product. We're forming a bond here. We have a ketone here. So again, beta keto ester. That looks horrible. And this came up before. If you have H3O plus and heat and you're using that on something where there's an ester beta to a ketone, the H3O plus is going to turn the ester into a carboxylic acid. You have a carboxylic acid beta to another carbonyl, and then you're heating it, so you're going to lose the carboxylic acid entirely because it's beta to a carbonyl. So what you're going to end up with is just the ketone because the carboxylic acid is gone. So this is another context where that last step just comes up. Anytime you have an ester beta to another carbonyl, if you do H3O plus in heat, you're going to lose the ester through decarboxylation. So now I will briefly talk about Michael addition. It's just conjugate addition, where you have a conjugated carbon-carbon double bond. Except in this case, the nucleophile that attacks it is going to be an enolate. So like you could have this kind of enolate attack there, where it's just one ketone. Or you could have this kind of enolate, or any other enolate, like it doesn't matter, just any enolate attacking a conjugated carbon-carbon double bond. That's going to be Michael addition. And I'm not going to show the mechanism, but I showed the general mechanism for conjugate addition with ketones and aldehydes earlier. It's going to be the same, just enolate is the nucleophile. And the carbon-carbon double bond can be conjugated with a carbonyl, like a ketone, an aldehyde, or an ester, or whatever. That's expected. It can also be conjugated with a nitro group, because this is conjugated. It has that same resonance form that leads to the same kind of reactivity. And the same thing can happen with a nitrile. So if you add enolates to these kinds of things, where you have a carbon-carbon double bond conjugated with a nitro or a nitrile, that'll do Michael addition the same kind of way. And one last thing about Michael addition is, like, if I take this substrate with these two esters beta to each other, I add a base, and then I add a conjugated thing. You're going to form an enolate here, and it's going to attack there, and then like you're going to do tautomerization, you're going to get the carbonyl back. I'm just going to skip to the product. I guess that's one thing I can do on Monday if you want. I can go over mechanisms like this in detail. I'm just trying to save time. But this is the product you would get. And if you number the carbons from like one thing, one functional group to the other, there's a 1-5 relationship. And you're always going to have this 1-5 relationship for Michael addition products. Doesn't matter where the carbon-carbon double bond came from. If it was conjugated with a nitrile, a nitro, or whatever, it doesn't matter what forms the enolate, you're always going to have this relationship if it is a Michael addition. So the last thing I'm going to talk about is Robinson annulations, and these are just a Michael addition followed by an intramolecular aldol reaction. I don't know when something will stop at a Michael addition and when it will keep going due to Robinson annulation, so I know that's a thing a lot of people are confused by. If you haven't already, you might want to email your professor, because I honestly don't know. Like I've said during workshops, I assume if they don't say draw the annulation product, you can just stop at Michael, but maybe there's some factors that will tell you when it will stop and when it will keep going. I am going to show an example of a Robinson annulation. So we're adding a base, we're going to form this enolate, and it is reacting with this conjugated ketone, so the nucleophile will attack here. We end up with this. This is our Michael product. Has that 1-5 relationship again. I'm not going to do the numbering because I'm going to have to number it for a different reason, but if you count them, you'll see there's a 1-5 relationship. But like I said, this is the Michael products. Now we're going to do an intramolecular aldol reaction. If you do the mechanism for a Michael addition, you'll see, actually, would be better, because you can't really reform it from H. But if you use hydroxide, you're going to reform the base catalyst at the end of the step. Like at this point, we have hydroxide again. We still have a base, so it can catalyze another reaction. So if we take the proton that's alpha to the ketone down here to form this enolate, and then we number this as carbon 1, and we go up to one of those other ketones, you can see that there is 6 carbons there. So if we do an intramolecular reaction, and I'm actually going to make this carbon 6, but if we do an intramolecular reaction, then you're going to get a 6-membered ring, and 6-membered rings are the most stable. And this is always going to be possible. If you do a Michael addition, you're always going to have like an alpha position. Well, maybe not always, but like if you're using a ketone conjugated with something, you're always going to have this option. So you can always do this intramolecular reaction where you form a 6-membered ring. So I feel like a majority of the time Robinson annulations are possible. It's just I don't know when it won't happen. But this is the intramolecular aldol step. And it's going to form a 6-membered ring. And it really, 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 really helps to number your carbons when you do these, because it's really easy to get confused when you have so many things, so many carbons in so many different places. So I numbered them before, I'm going to number them again. There was a ketone on carbon 2. At carbon 5, there is this part with the other ketone coming off of it, so you can see that kind of on the bottom. We formed a bond between carbon 1 and carbon 6. You can see that's this bond that formed. And then there's a methyl group on carbon 6 along with the alcohol. And Robinson annulation keeps going, and it's going to form the condensation product with the carbon-carbon double bond. So that's just going to be a carbon-carbon double bond between carbon 1 and carbon 6, and we're still going to have this ketone. So if you're doing Robinson annulation, number your carbons, and just remember it's Michael addition followed by intramolecular aldol. It's always going to be those 2 steps in the same order. And if you're working backwards, like you're given this structure and you have to figure out what did you start with, break this bond, because that's the bonds that forms for the intramolecular aldol reaction. And if you work backwards by breaking that bond, you should be able to figure out by like kind of numbering your carbons and working backwards, this was the Michael product. And then it would make sense if this green bond was the one that formed, because that's where an enolate would form here, because it's between two carbonyls. And then if an enolate forms there, there was probably a double bond here. So yeah, just those kinds of steps, identifying which bonds are being formed or broken, going backwards, and then what that means for the starting materials could help you figure it out. If that's something people want me to cover on Monday, you can come and ask and maybe come with a question for me to cover or something, but that's where I'm going to stop. If you want me to talk about polymers to review, I can do that on Monday, but I don't think I'm going to do that, especially because you covered it in the last week, basically. So hopefully this was helpful, and I will see you guys for review, probably. Good luck.